Hello to everyone. Welcome to the course on Numerical Linear Algebra and Application. Today we are going to learn 43 lecture of this course. In the previous lecture, we did some iterative procedures, Gauss-Jacobi method, Gauss-Seidel method. In contrary to these two methods, we are going to learn some few examples on successive or relaxation method. This method is a generalization of the Gauss-Seidel method. This method is often used when the coefficient matrix of the system of equations is symmetric. We define an auxiliary vector x cap as x cap of k plus 1 will be equivalent to minus of d inverse L of x of k plus 1 minus d inverse of u of x of k plus d inverse of b. So the final solution can be written as x of k plus 1 will be equivalent to 1 minus w times of x of k plus w times of x cap k plus 1. Upon simplifying these two things, we do get as x of k plus 1 will be equivalent to d plus wl whole inverse 1 minus w times of d minus w into u x of k plus w times of d plus wl inverse of b. So this can be written as h of x of k plus c, where k is equal to 0, 1, 2, etc. And this h can be written as h is equal to d plus wl whole inverse 1 minus w times of d minus w of u. And c is equal to w times of d plus wl whole inverse times of b. So this equation 3 can alternatively be written as x of k plus 1 will be equivalent to x of k minus d plus wl whole inverse times of d plus wl minus 1 minus w of d plus w of u x of k plus w of d plus wl whole inverse times of b. So this can be written as r of k is equal to b minus ax of k is the residual. R of k is equal to b minus ax of k is the residual. So we may write it as v of k is nothing but w of d plus wl whole inverse r of k. So this can be written as d plus w of l multiplied with v of k will be equivalent to w of rk. This equation describes the SOR method, that is successive over relaxation method, in its error format. For computational purposes, it is convenient to use this equation. When w is equal to 1, that is, we call it as a w, and some of the textbooks they do write it as omega. Whatever is the case, this w is called relaxation parameter. This is relaxation parameter. Relaxation parameter. Equation 4 reduces to the Gauss-Seidel method. The quantity W is called the relaxation parameter. So this W or omega, whatever we call it as, relaxation parameter. Now, and using this, we can write the updated approximation as, when 0 is less than W less than 1, if W is greater than 1, then the method is called over relaxation method. So when W is greater than 1, the method is called over relaxation method. When W is less than 1, then it is called under relaxation method. So when W is greater than 1, it is the over relaxation. When W is less than 1, under relaxation, and W is equal to 1, it turns out to be a Gauss-Seidel. Let us look at into some very practical example. Let's say I have a 2 by 2 matrix, that is 1 minus a 1 multiplied with x1 x2 will be equivalent to b1 b2, where a is a real constant, for which values of a, the Jacobi and Gauss-Seidel method converges. Now the question is, what are the values of a such that the Gauss-Jacobi and Gauss-Seidel method gets converges? For a is equal to 0.5, find the values of W which minimizes the spectral radius of the SOR method. Let us look at it in the first example. The Jacobi method becomes x of k plus 1 is equal to h times of x of k plus c, where h is equal to, that is 0, a 0. The eigenvalues of the Jacobi iteration matrix H is given by mod of H minus lambda I will be equivalent to minus lambda a minus lambda. That will be equivalent to lambda square minus a square is equal to 0, which implies lambda plus a times of lambda minus a is equal to 0, lambda is equal to plus or minus a. Or you can write it as the spectral radius of the Jacobi iteration matrix becomes, that is rho of h of j will be equivalent to absolute value of a. Therefore, the condition for the convergence of the Jacobi iteration method, that is less than 1. The Gauss-Seidel iteration method becomes, that is 1 0 minus a 1 multiplied with x of x plus 1 will be equivalent to 0 a 0 0 x of k plus b1 b2. Or you can write it as x of k plus 1 will be equivalent to 0 a square multiplied with x of k plus 1 0 a1 multiplied with b1 b2. So the eigenvalues of the Gauss-Seidel iteration matrix are given by norm of, or given by modulus of h minus lambda I. H is the 2 by 2 matrix as we discussed in the previous case. Lambda is a scalar, I is the unit matrix. So h minus lambda I will become mod of minus lambda a 0 a square minus lambda, which will become lambda times of lambda minus a square is 0. The spectral radius of the Gauss-Seidel iteration matrix becomes rho of HGS is equal to a square. Thus the convergence we require is, that is modulus of a is less than 1. That is, the optimal relaxation factor for the SOR method is given by W of optimal is 2 times of 1 minus mu square upon mu square, that turns out to be 2 times of 1 minus square root of 1 minus a square upon a square. So when you simplify this, it turns out to be 2 upon 1 plus square root of 1 minus a square. So which is approximately 1.0718. So we will look at into the second example. For the solution of the system of equations, set up the SOR method, find the optimal relaxation factor and the rate of convergence. Perform 3 iterations of the SOR method for the above equations. Take the initial approximation as x of 0 as 0, that means x of 1 is 0, x of 2 is 0, x of 3 is also 0. So then for the sake of brevity, we see the exact solution is x of 1 is equal to 6, x of 2 is equal to 5, x of 3 is equal to 3. And we have the lower triangular matrix L is equal to 0, 0, 0, minus 1, 0, 0, 0, minus 1, 0. And diagonal D is equal to 2, 0, 0, 0, 2, 0, 0, 0, 2. And upper triangular U is equal to 0, minus 1, 0, 0, 0, minus 1, 0, 0, 0. So we will have the SOR method is x of k plus 1 will be equivalent to h times of successive relaxation x of k plus some constant c. So that becomes 2, 0, 0, minus w 2, 0, 0, minus w 0, whole inverse, multiplied with 2 into 1 minus w, w dot 0, 0, 2 into 1 minus w, w, 0, 0, 2 into 1 minus w. So when you take the inverse of this, right, so inverse is nothing but transpose of cofactor matrix. That is 2 into it will go, so 4 minus 0. So like that, if you do all those things, you will end up with an inverse given over here. Multiplied with the same matrix, and since it is a 3 by 3, this is also 3 by 3, you will have a matrix of the form like this, right? So you have the matrix of form like this. Look at here in all these cases, so when omega is 1, so this complete column will be 0. And we calculate C, that is W of D plus WL whole inverse of B. So you get W is equal to in this form 1 by 2 0 0, W by 4 1 by 2 0, W square by 8, W by 4 1 by 2 multiplied with 7 1 0. So this will be 3 rows 1 column. Hence we will have x of k plus 1 will be of this form. That is 1 minus w, w by 2 0, w times of 1 minus w by 2, 1 minus w plus w square by 4, w by 2, w square times of 1 minus w by 4, w into 1 minus w by 2 plus w square by w cube by 8 plus this value. So ultimately, and the c value will turns out to be this one. So upon simplification, you do get as the matrix like this. The iterated matrix associated with the Jacobi method is given by minus of D inverse, that is 1 over 2 0 0, 0 1 over 2 0, 0 0 1 over 2 multiplied with 0 minus 1 0, minus 1 0 minus 1, 0 minus 1 0. So you will get the matrix like this. Now Hj minus lambda I will be this matrix. So ultimately you will have the matrix like this, minus lambda times of lambda square minus 1 by 2 is 0, which implies lambda is equal to 0, lambda is equal to plus or minus 1 over 2. The spectral radius of the Jacobi iteration matrix is, that is mu is equal to 1 over root 2. The optimal relaxation factor of the SOR scheme is W of optimal will be like this after the computation. that is 2 over mu square times of 1 minus square root of 1 minus mu square, which turns out to be 4 times of 1 minus 1 over square root of root 2. So ultimately it would be 1.171573. When W is equal to W optimal, we will have a rho H SOR will be like this. The rate of convergence of the SOR method is V is equal to 0.7656. Substituting the values of W optimal is 1.1716. The SOR iteration scheme becomes like this. That is x of k plus 1 is equal to, that is minus of 0.1716, 0.5858, minus of 0.1005, 0.1716, 0.5858, minus of 0.0589, 0.1005, 0.1716. So starting with x0 is equal to 0, so we obtain x of 1 this matrix, and x of 2 is this matrix, and x of 3 is this matrix. So for the second example, we write the SOR scheme as D plus WL times of V of k is W of RK, that is W of t is 1.1716. And we write this R of k as B minus AX of k, x of k plus 1 is equal to xk plus V of k. Starting with x0 is equal to 0, we obtain the R0 like this. So R of 0 is 711 and V of 0 is 4.1006, 2.9897, 2.3361, and this is x1. And this R of 1 turns out to be 1.7867 and 1.4609 minus of 0.6843. So and V of 1 will become 1.0466, 1.4689, 0.4596, and x of 2 will become 5.1472, 4.4568, 2.7957. So R of 2 will be like this, and V of 2 will be like this, x of 3 will be like this. Iterative method to determine A inverse. Suppose that we know the approximate inverse B of matrix A, then AB is not equal to I. The error matrix is given by E is equal to AB minus I and AB is equal to I plus E. From equation 5, we will write A inverse as B times of I plus E whole inverse, that is equal to B times of I minus E plus E square minus E cube plus E power 4, etc. So as we see, norm of E is less than 1. So the approximate equation 6 we will have A inverse is equal to B times of 1 minus C, which turns out to be B times of 2I minus AB. So the iteration method gives you the form of given in equation 7. That is B of k plus 1 turns out to be B of k, that is 2I minus AB of k. So pre-multiplying you get of this form like this, AB of k plus 1. Or we can write it as I minus AB of k plus 1 is I minus 2 times of AB of k plus AB of k twice. So you can write it as I minus 2 ABK whole square. Hence, the convergence of the iterative method is a quadratic. So what we learned in this particular lecture is how actually the convergence of iterative method takes place. So we have seen that the convergence of the iterative method is a quadratic convergence. You can see from this example also, let us take the inverse of the matrix of this 2 by 2 matrix. Using iterative method, this gives you an approximate inverse as like this. Suppose if you perform only 2 iterations, let's see that. So B of 1 is equal to 1.8, minus 0.9, minus 0.9, 0.9, multiplied with 2002, minus of 0.90, 0.9, which turns out to be matrix of this form. That is 1.98, minus 0.99, minus 0.99, 0.99. So similarly, second iteration b of 2 will become like this. So you get the approximation like this. So if you look at this exact inverse for this matrix by usual methods, that is 2 by 2. So 1 by AD minus BC and DA minus B minus C. If you do that, so the exact one is 2 minus 1 minus 1 1, whereas this turns out to be this. That means if you perform only 2 iterations, you are getting to very close to the exact solution. And if you perform 100 iterations, almost all you do reach to the exact solution. So in this today lecture, what we learned is how actually the iterative method converges, and I proved that the iterative method is a quadratic convergence. So I will stop over here. Thank you for listening to this convergence of the iterative methods. Thank you once again.